In this video, I will talk about three very important terms in heap. They are arena, chunk, and beans. Recall that in previous 2 weeks, we have talked about heap and we have talked about T-cache structures. If you still remember, we mentioned that in heap, it is a specific type of memory that lives inside the memory location of a process. And then T-cache is a specific type of data structure that keeps those chunks, especially those chunks are coming from one same thread. So T-cache is the name for per thread cache. However, you may find that there's something missing between the heap and the T-cache layout. So the question is how glibc manages heap and how to store those information regarding the T-cache inside the heap so that glibc will always know the relationships of those chunks and the beans of T-cache and to release them or to allocate or to free those chunks very easily in a high performance and also is in an effective manner. In order to understand that, let's start with the topmost term, arena. Arena is a data structure that stores the necessary information in terms of the heap. libc has to know where the heap is so that libc is able to manipulate the memory on heap. In order to let libc know about the current heap, libc has this data structure called arena, which stores in the data segment of libc. Arena is composed of multiple components. If you're using Pounded Back, you could just type arena in order to get all the fields, such as fast bean, those beans, and then the current size of the heap. Also, as main underscore arena is a symbol in libc.so, you could just use DQ, which means to dump, with the address of the main arena, and you'll be able to get those dumped bytes information starting from the address of main arena. And those information should be corresponding with the information that shows using the argument, the command of arena. In dlmalloc, which is the ancestor version of the current malloc that is used in glibc, it has only one arena. As a result, if there are multiple threads, and then for those multiple threads, if they are using the heap, then they have to wait for each other to finish the operation, which is really costly in terms of performance. Therefore, ptmalloc2 was created and it can handle heap for different threads. The way that it works is that it's going to create a heap for each thread. Of course, there is a maximum threshold, but we're not going to talk about that today. All you need to know for our course is that for ptmalloc2, the heap is per thread. Similarly, the arena, which maps to the heap information, is also going to be per thread. Actually, for ptmalloc2, each thread, if possible, will have an arena, and then the arena will point to different other arenas, as well as the heaps that is related to this current arena. The arena that is corresponding with the main thread is called a main arena. And that is why you can use main arena to get those information. Also, because there might be multiple arenas, those arenas, they're going to chain together so that you can find the other arena from one. And that is why if you look at the information of arena, you find this particular field called next. And for this field, it's going to point to the main arena. And starting from there, the main arena is going to point to the other arenas. And in this case, because we have only one arena, the next is the same of itself. So it is still main arena. For more about per thread arenas, I recommend you to look into this link, which is a wiki about the malloc internals for glibc. You can also just Google per thread arenas, and you will get a lot of information which is useful for you to understand in depth. In our class, we're going to focus on only one thread. So we're going to only have one arena throughout the security setup in our course. Now let's start with the arena and look at those fields inside an arena. So as I mentioned before, we found that there are a long list with the name of beans. These are the beans that are analogous to Tcache bean, but it's different. And if you use vis, this command in back, you'll be able to get the Tcache bean, because Tcache bean stores into the heap. However, for the other beans, the information regarding the beans is actually stored in arena. In fact, for heap, usually there are 5 different kinds of beans. Originally, glibc only has small beans and large beans. Starting from v2.3, and stored bean is created. Also, fast beans are created. These 2 beans are used to speed up the performance of heap allocation and free. And then later on, starting from glibc 2.26, Tcache beans are created. Also, Tcache bean is used in the purpose of improving the performance of management of memory. The high-level structure of those beans looks similar. However, there's still some small differences for each different kinds of beans, and I will talk about them in future. Other than Tcache beans, the other 4 beans will all recorded in the data structure of arena. For fast bean, it has a specific field in arena which is called fast beans Y. And for the other beans and sorted beans, small beans and large beans, those are stored into the field of beans. And this is why if you look at beans, you will find a long list of them. For fast bean, they are similar to Tcache beans in the sense that each bean stores the chunks with the same size. And it's different from Tcache bean in the sense that the size is going to be different and the number of fast beans are different. For X64, fast beans is composed of 7 beans from the size of hex 20 to hex 80. So there are only 7 beans in total, which is different from Tcache beans. However, if you go back to the arena information, you will find actually there are 10 entries for fast bean. Yet for X6, it only uses 7 is because the number of fast beans and the size of maximum fast beans size is configurable. So you can make fast beans starting from hex 20 to hex 80, which is by default. You can also enlarge that so that you can have hex 90, hex A0, and then hex B0. But you can only have 10 at most. For the other 3 types of beans, which are unsorted bean, small beans, and fast bean, they all stored into arena beans field. There's only one unsorted bean. Unsorted bean is used as a transition point where all the free beans will go to unsorted bean first, and then go to small beans and large beans. There are 126 beans in arena beans in total, and the first bean is unsorted bean. Starting from bean number 2 to bean number 63, which is 62 beans in total, they're all small beans and therefore chunks with the size that is smaller than 1024 bytes. Small beans are also similar to Tcache beans and fast beans in the sense that each small bean is storing the chunks with the same size. So for bean number 2, the small bean is going to store the chunk with the size of hex 20. And similarly, the third bean is going to store the chunk with the size of hex 30. And then for the 63rd one, is going to store the chunk with the size of hex 3F0 bytes, which is 1008 bytes. So you may wonder that why are there so many beans with this very similar layout, and what is the purpose of having all those different types of beans? The reason is because performance. Accessing T-cache beans is faster than accessing fast bean. And also accessing a fast bean is faster than accessing a small bean due to the data structure layout. Therefore, glibc, when it designs the data structure, it wants to have a hierarchical layout for those beans such that those chunks, when it's free, can go back to recycled as soon as possible. Because recycling those chunks coming from T-cache or fast beans is going to be faster than recycling from small beans. After we're talking about unsorted bean and the small bean, now's the time for us to talk about large beans. So large beans are for chunks over 1,024 bytes. Different from any other beans, large beans is not going to store chunks with only one size. Instead, it's going to store chunks within a size range. Starting from bean number 64 to 126, the first large bean is going to store the chunk with the size of from hex 400 to hex 440. And similarly, it's going to store all those different chunks. And specifically, for bean number 64, from 64 to 95, the range here, if you look at the table, you find that the range is always hex 40. So each bean is going to store the chunk with the size of the step of hex 40. And after size 95, it's going to increase this interval. So it's going to increase the length from hex 40 to hex 200. This hierarchy will keep going. And in fact, if you look at this table again, we will find that for the first 32 beans, the size range is always hex 40, which is 64 bytes. And then starting from the 33rd one to 48, which are 16 beans, the length of interval is 512. And similarly, the later the bean number is, the bigger the length of the internal is. And for the last bean, it's going to store all the remaining large chunks. glibc has a nice description in terms of those beans inside the source code. If you just use this link, you'll be able to access the source code of glibc, and you'll be able to find this explanation in the comment of malloc.c file. Now we already know how the beans look like, and we also know that there is a hierarchy in terms of the different types of storage inside the heap management, so such as T-cache beans, fast beans, unsorted beans, and small and large beans. So now let's talk about how glibc handles array and malloc instructions. And specifically, when I say instructions, it really means that just the operation. It's not really an x86 or x86 64 instructions, just in the function that calls array or called malloc in glibc. And this is very important, but you don't have to remember this. Or for me, like I don't remember all the details in terms of free and in terms of malloc. But it's nice for you and also like for me, when I do this, I just like remember the high level order of how those beans are used, which one is the first one to use, if the first one is not used, which one is the second, so that we will be able to understand the tier of the heaps, and also the tier of the beans, so that it will help you to generate an attack in the future if you have a specific targeted bean. Okay, so now let's start with fray first. The reason why I want to start with free is because later on when you look at Malloc, you will realize that actually a lot of information, a lot of like the chunks, those arrangements coming from a freed list. So now I'm going to start with free, and then depending on the information that we get from the current free list, then we're going to talk about Malloc. Cool. So for free, the first step is that we're going to recycle a chunk into the T cache. So if we are freeing a chunk, and also if the chunk is within the size range of a T cache, remember for x6, that is from hex 20 to hex 410, then we're going to store in T cache. And of course, we have to have enough room that is available in T-cache bins. And remember that for T-cache bin, each of the bin can hold up to 7 chunks. So the first choice is going to be T-cache, same thread cache. And if there's T-cache, there's no space in T-cache, then it's going to recycle to fast bin. Fast bin is like the second tier, or the second prioritized option for the free chunk. So if the chunk is small enough, it will store into a fast bin. And also keep in mind that there is only 7 fast bins for x64 by default. It has already the size from hex 20 to hex 80. And then the third is if the chunk was M mapped, this is like a specific flag, but we're not going to cover this in our course. We just always by default set that no chunk is allocated through a map specifically. So this rule doesn't apply, but in general for glibc, this rule apply. And then the fourth step is going to do coalesce, meaning that we're going to combine those free chunks together, combine them into one, just in case that we can use those chunks from small size to a bigger size, put them together in case that in the future, if there is a larger chunk required by Malloc, we can just use this chunk that we put them together through all those free small chunks. So if a chunk is adjacent to any other free chunk, now we're going to do a coalesce. We're going to combine this chunk with those other adjacent chunks together. After that, we're going to put the chunk into a sorted bin. So a sorted bin, again, is the bin that is not assorted and with arbitrary size of chunks, but it will remember the size of a chunk by using the metadata stored in the free chunk. But if the chunk is in the top chunk, which is the heap information. If you use this, you will see that at the bottom of the heap, which is like the highest address from the heap, you will see top information. So if the chunk can be merged into the top chunk, then it will go to the top chunk directly. Otherwise, it will be stored into a sorted bin. Then the final step is to check if the current top chunk is large enough to return back to the OS. Remember that there is a possibility that the current heap is not large enough, so that the system is going to allocate another heap to the current arena, to the current thread. So if the heap has multiple heaps in the arena, then we may want to consider, by the time the program is running, we want to consider if we still need that large amount of heaps. And free will help us to reconsider that. So we will consider that if the current fleet chunk is large enough, then we're going to coalesce the fast bins and then check if the top chunk is large enough. And if the top chunk is large enough, then we're going to return those top chunk into the back into the system, so that we're not going to have those a lot of memories for heap. However, this operation, notice that it might be deferred because, returning the memory back to the heap is gonna be time consuming. And sometimes it's not really that critical, like time critical. You probably don't really need to do that right now. So that's why sometimes this operation will be deferred due to performance reasons. And then if it's deferred, then this may be happen during a malloc or the other memory-related call, such as realloc. All right, so that's pretty much for free. And now given those free information, now let's take a look at how glibc handles a malloc requirement. So for malloc, the first step is also similar to free, is that we're going to look into Tcache. We're going to check if there is any available chunk from Tcache, and if so, we're going to reuse it. And then the second is actually for mmap, which we're going to skip it for our course. After that, then we're going to get a lock. And remember that originally we said about arena, and that we mentioned that arena is kind of thread-based if there is not too many threads, right? So if we already check our Tcache, if there's nothing available over there, now is the time that we are gonna touch the part that is gonna be like thread only, and also that is something that is gonna related to arena. So we're gonna touch the content from arena, and that is like thread specific. So now for us, we need to get a lock for arena so that we can start to change arena's content. So in this case, then in the third step, we're gonna first try to recycle any chunk from fastbin. So we want to return a suitable fastbin chunk if it exists. And also, when we return a fastbin chunk, we also want to check that, for this specific fastbin, if there's more chunks over there. And also, if the chunk, if this is something that we can put back to Tcache. Usually, by the time that we use fastbin chunk, it's already mean that we don't have anything from Tcache. That's why we, didn't manage to get anything from Tcache. We go from the first step to the third step. So in that case, we're gonna preview Tcache if there's still more chunks coming from Fastbin. But also, when you're doing this, you only look at the specific fastbin, the bin with the correct size that the program is requiring in terms of the chunk. So you're not gonna touch the other fastbin, you're only gonna touch the one fastbin, which is the one with the exact same size of the one that you're requiring. So keep it in mind of that, and that's why we are, we're gonna review Tcache as we go through the fastbin. And also, I think for this specific type, and especially for this specific step, you want to keep this in your mind. You want to remember that, because later on when we talk about fastbin, and then when we talk about fastbin related attack, we will use this Malloc rules very frequently. Okay, and then if fastbin doesn't work, then we need to find a suitable chunk from small bin. So then now we're going to just look into the small bin and see if there is any chunk available. And again, for small bin, remember that small bin contains each bin with the exact same chunk size. So it's going to be very easy. You're going to just like look into the small bins, go to that specific bin, and then check if there is any chunk available. And then after that, what we're going to do is to resolve all the deferred frisk coming from unsorted bin. So remember from free that we are going to put all those, freed chunks once it's like, if it cannot be put into Tcache, if it cannot be put into fastbin, then we're going to just dump them into unsorted bin. But we are not going to deal with it until there is a malloc that will need us to resolve the deferred phrase. So this is kind of like lazy coalition, or say lazy merging, lazy and sort of being cleaning up, putting that into the small and large bins. So at this point, we're going to resolve all the deferred phrase. And the way that works is that we'll first go to fast bins. Actually, it will move all those fast bin content into a sorted bin. So by the way, by the time that it cleaned up, it will just clean up very thoroughly, in the sense that it will start from the fast bins, move those fast bin content into unsorted bin, and then, so this is this step, right? We move fast bins content into unsorted bin, and then we're gonna start from unsorted bin, move those content. We're gonna coalescing and also move them into small and large bins. So notice that when we do the movement from fast bin to unsorted bin will already start to coalesce. So remember that when a chunk is free, we store prev in use and pre-size into the chunk. So we are actually using that to identify if there is any chunk that is next to our current chunk and it's also a free. So that's why we want to store those metadata inside the chunk of the heap. And because of that heap metadata, it improves the performance. Also, as you already know, because of that heap data information, it can be modified by users. So it's like because of a winning in performance, now we are in a potential vulnerable situation where attacker can somehow manipulate the heap layout information, which causes heap corruption. All right, so starting from there, we already moved fast beans to unsorted bin, and then we're gonna move chunks from unsorted bin to small and large beans. So the way that it works is that we're gonna go over the chunks from unsorted bin and then put them into small, large beans until we find a chunk with the exact size. So here is that we're gonna put those beans with the exact size. That is a very important keyword. It's the same size. So this is the only place that you put chunks into the small and large beans. Then looking to the large beans, what libc is going to do is that it will find a large enough chunk for a large request. So right now, if the request is large, meaning that the request is greater than 1024 bytes for x64 infrastructure, glibc will search the appropriate large bean and then successfully, large beans until a large enough chunk is found. So it will go through the large bin, and remember that large bin are bins, for chunks within a range of size. So it's gonna just go through those bins and then find a large enough chunk, so that we can, use that chunk to cut it into a smaller part, and then to use that chunk to fit with the request of the current large size of Malloc. And here, just note that when we resolve all the deferred phrase, we also try to see if we can find a chunk that fit with the request of Malloc, right? But when we resolve all the deferred phrase, we're going to find a chunk with the exact same size. So at this point, we still hope that we don't have to cut a large chunks into small pieces. So here we still try to find the chunk with the exact same size. However, if we cannot find a chunk with the exact same size from this step, then we move on to the next step, and here we just find a large enough chunk. So as long as we find a chunk that fits with the current request, then we're gonna stop over there, and then we're gonna use this chunk. But the way that we use it, we need to cut it into the smaller one, because say if the large enough chunk is with the size of, I'm gonna put a numbers, for example, hex 2K, right? However, if the requested chunk for us is say 1/800, and that is also in hex for that bytes. Now we're going to cut this into, a hex 20 and a hex 1800. We're going to give this back to the malloc, return that. And then for this part, we're going to put it back into the corresponding bin. And then finally, if none of the previous steps work, that means that we really need to go look into the top chunk, which is like a big chunk that is currently still available. So we want to start to cut the part from the top chunk and then return that back to malloc. And if top chunk even not large enough, that's the moment that we need to enlarge top. So that's why we want to have probably like extra heap, so that we can use a new heap to allocate this specific required malloc. All right, so that's pretty much about beans. So far we have talked about arena, and we also talked about beans. So arena is a larger data structure, and then inside arena there are all different kinds of beans. And now let's talk about chunks. So turns out that for different beans, the chunk that is storing in each of the bin also has different data structure, and the layout is slightly different. So remember that we talk about T-cache, right? And then we talk about chunks inside the T-cache. If you still remember this picture from a previous video, you will be able to understand what's talking about here. So we usually consider the data structure of the chunk by considering two different situations. One is the chunk is allocated, and the other is the chunk is freed. So when the chunk is allocated, then this chunk has like 16 bytes at the beginning, which contains a bunch of zeros, followed by the chunk size and the flags. And those flags contains information such as whether or not the previous chunks is in use, as well as the size of the like the chunk size. It is for the current chunk. And if you remember this part when talking about Malloc, now you probably can have a better idea of why we want to record such flag prev in use in the current chunk. This is because that we want to use this current chunk's information to tell us whether or not we want to look at the previous chunk, so that we want to combine these two chunks together into a larger chunk. Cool. So right now, we know about the allocated chunk, and then similarly for freed chunk, when a chunk is freed, then we want to store an actual information, which is the forward pointer, meaning that if the chunk is freed, then what is the next chunk that this freed chunk is points to? And remember that in Tcache, the forward pointer, it will always point to the start of the data part of the other chunk. So if we look at the chunk, if we look at the allocated chunk, or like also just the free chunk, we know that it starts with this here, right? So that is the start of the metadata, which is also the start of the chunk. And the data actually starts from here. This is where data starts. And in fact, if you do malloc, it will return the address of where data starts. So for Tcache, when it stores the forward pointer information, it will point to the start of data. And this is different for the other types of bins, which I will show you in the following. So for fast bin, still it's going to store forward a pointer when a chunk is freed. But in this case, now it's going to point to the first part of the chunk, which is the the head of the chunk, the first byte of the chunk. So it's no longer this place. Here there is a 16 byte difference. So it's gonna be point to the start instead of the data. So that's why if you look at free chunk, and then if you look at the free chunk for for fast beans and for Tcache beans, you will realize that actually the address stores is slightly different. And here is exactly the reason why it's different. Even though the fast bin is moved, like the chunk is moved from fast bin back to the Tcache bin. Then for small bean and for sorted bean, the difference is even bigger. Besides, storing FD forward pointer and always point to the start of the chunk, now it's gonna use this first 8 byte to store the previous chunk's size. So remember that. Now let's take a look at back to malloc. Right, so in malloc, we will need to use prev in use and prev size. This is the way that you know whether or not the previous chunk is something that you can correlate it, you can combine together. So that's why in assorted bin and also in small bin, it stores this information of precise. And then when you have forward pointer, you want to point it at the start because you want to get the information at the start of the chunk. You do care about that information for the future combination. So that's why you have this. And also there is another pointer, which is called a backward pointer. So different from fast bin, and T-cache bin, where the bin is basically a single direction list. So if you remember, let me just draw over here. For bin, say T-cache bin, right? So it's gonna be this bin with the size hex 20, for example. It's gonna point the chunk and then point to the next chunk all the time. And then for fast bin, it's similar. The only difference is that right now the chunk is no longer be like pointing to the data part. It's gonna be pointing to the metadata part, which is the actual start of the chunk. But here, for a small bin and for unsorted bin, the chunk is gonna be point each other. So in a sense that it's gonna have a like bidirectional link inside each bin. So the reason why we want to have this is because like for unsorted bin, as I mentioned, they're not sorted. So we hope to move back and forth to be able to get all the chunks easily. So that's why we want both a forward pointer and backward pointer. And then even further in large bin, we store even more information when a chunk is freed. So it's not only just a forward pointer and a backward pointer, it's also the size of forward and backward. And the reason is also because that for large bin, you don't know the chunk of the current or the previous chunk that is connected within the same bin, because in large bin they're going to store all the bins within the similar range into a same bin. So that's why even within a bin, it's possible that chunks are in different sizes, and we want to use the FD size and the backward size for us to track the information. And we don't really want to really like get this size by having to go from a forward pointer to that specific chunk, and then from the chunk you read the chunk size, because this is gonna be more costly than if you just like store the chunk size over here and directly access the size of the forward chunk by looking at the current chunk's information. And then, as I mentioned, in terms of those link, the free list for inserted small and large bins, it's going to be bi-directional. So what it means is that in Arena, which is also like the main arena, if you use main arena, sorry for the typo, main arena in Pondyback, you will be able to get the symbol. So if you look at arena and then if you look at bins, you will find that each bins is actually 16 bytes. So there are two elements in each bins, like the data structure of each bin. One is forward and the other is backward. And because we are doing x64, so that is 60-bit, 64-bit, which is 8 bytes. So that's why we have 8 bytes to store the forward pointer and another 8 bytes to store the backward pointer. And then starting from the head of the bin, we're gonna have that point to each chunk. And also the each chunk is gonna point back to the previous chunk using the back pointer. And also for the head, it's gonna use the backward pointer to point to the furthest, or say the endmost chunk. And similarly, for the farthest chunk, it's gonna use the forward pointer to point to the start of the free list. All right, that's pretty much for the data structure of heap. And just to quickly recap, we have talked about 3 different kinds of data structures, which are arenas, bins, and chunks. So arena has main arena and other kinds of arena. And usually each arena represents for one thread. There are cases that, one arena may take charge of multiple threads, but usually in our case, we're gonna just handle, main arena only, since for our course, we're gonna focus on single thread. But just for your information, it's possible that arena can take care of multiple threads. Then from arena, we know, there are beans in one arena, and beans are in also different types. There are T-cache beans, fast beans, and sorted beans, and then small and large beans. And they are in a hierarchical structure, and this really helps in improving the performance of freeing a chunk and then like mallocing chunk, like those memory management inside the heap management. And finally, we talk about chunks. And we know that chunks in different bins are in slightly different data structure. So it looks similar, but for assorted bins, small bin, large bins, there is extra information, especially for large bins, has even more extra information. And also for each different kinds of chunks, they connect to each other, because this will be very helpful for us to identify those currently available. When I say available, it means free, like those freed chunks that can be recycled. But in assorted small and large bins, the list is bidirectional, which is different from fast bins and T-cache bins, which is only like single directional in free list. So yeah, that's pretty much for the data structure of heap. I hope that this will be helpful for you to understand how heap works, and especially in the future lecture, we're going to talk about security vulnerabilities for all the other kind of beans and all the other kind of chunks. And the reason why I didn't talk about this at the start of our heap series is because I feel that this might be a little bit too overwhelming. And you may wonder that why there's so many chunks and why they're so different. I think that by the heap, starting the heap by introducing T-cache first, giving you a simple or a basic impression for how heap works on the high level will help you understand those very detailed information. And now we kind of officially kick off for all the information about heap. And starting from this lecture, we're going to talk about vulnerabilities from other beans, from other chunks.